I welcome you all to the session of engine system and performance, and today we shall discuss about variable geometry turbines. In the last class we have discussed about turbochargers, and pertaining to the operation of turbochargers we have discussed about two different types of turbines. The first category is known as fixed geometry turbine and the second one is variable geometry turbine. We have discussed about the problematic issues associated with the operation of fixed geometry turbine in the context of turbocharger or turbocharging. Now, if we recall, what we could discuss in the context of fixed geometry turbine is, from the name itself we can understand the geometry of the compressor as well as turbine is fixed. So, fixed geometry turbine. So, turbocharger, which is essentially a unit in which there will be a small turbine. Depending on the requirement, we may need to incorporate aftercooler or intercooler after the compressor certainly, but turbine and compressor, these two rotating devices are connected to a common shaft. So, if we recall, we have discussed about fixed geometry turbine. So, or in short FGT, we have discussed that fixed geometry turbines associated with a few problematic issues with the operation of turbocharging unit or turbocharger. What are those? You know that using fixed geometry turbine, if we need to boost the pressure ratio for a wide range of engine speed, turbochargers need to be operated at high pressure ratios and at high rotational speed for a wide range of flow rates. And while we are trying to operate turbochargers at high rotational speed to have high pressure ratios, two important issues should be taken into account, because these two issues are very detrimental for the operation of turbocharger. And these two problematic issues are, one is over speeding, number two is overheating. We have discussed these two detrimental effects in the previous class, and let me just discuss these two problematic issues once more. Overspeeding, you know that this is associated with the high speed of both compressor and turbine. So, this is basically fixed geometry turbine. If we need to have high pressure ratio to be produced by the compressor, compressor speed should be high. To have higher speed of compressor, turbine speed also should be high. That is the concept that we have discussed. Now, at high or higher speed of compressor and turbine, and rather high compressor and turbine speeds when subjected to high temperature of exhaust gases. So, basically exhaust gases are allowed to pass through the turbine. So, when turbine blades are exposed to high temperature exhaust gases and turbine is designed to produce high pressure ratio, while compressor is designed to produce high pressure ratio, so turbine speed will high. Revolving components of both these units will be destroyed because of this speed. So, high speed of both compressor and turbine when subjected to high temperature of exhaust gases can destroy revolving components of the turbocharger. So, this is known as overspeeding that we have discussed. What is overheating? The sole purpose of having this unit, whether it is a supercharger or turbocharger, is to increase the inlet pressure. Now, when inlet pressure should be higher because of this compressing the intake or incoming air, the pressure of that air or pressure of the charge will be further compressed in the inside the cylinder during compression stroke. So, the pressure will be even higher at the end of the compression stroke, which is accompanied with higher temperature as well. So, if the intake or inlet air pressure is higher because of higher speed of the turbine or compressor, in the subsequent stages of operation, temperature of the charge or incoming air will be more, and that high temperature may become vulnerable to several parts of the engine. So, this is known as overheating. So, essentially you can understand turbine or fixed geometry turbine which is used in turbocharger cannot be operated at high speed, otherwise these two problematic issues will arise, and rotating parts or several parts of engine will be non-functional rather. So, what we need to do? We need to reduce the speed. Again we have discussed in the context of supercharger, in fact taking the help of performance map, we had seen that if we reduce the turbine speed, certainly compressor speed will be reduced, because these two elements are connected to a common shaft. So, when compressor speed is getting reduced, compressor operation is limited between two different lines. If you can recall, the one line is which is extremely right side of the performance map is known as choke line. So, compressor cannot be allowed to operate beyond that line, otherwise compressor is said to be choked. Now, similar to what you have studied in the context of nozzle. On the other hand, when compressor is operating or operated at a low speed, then the compressor operation can meet surge line. So, even when compressor operation is approaching surge line, it is not desirable at all, because this situation will not desirable, because compressor operation will be highly unstable, flow reversal will be there. So, that means we can understand that using fixed geometry turbine we can have only high speed, then these two problematic issues will arise. If we allow the turbine to run at a low speed, then compressor operation can be unstable, as it can approach to the surge line. So, accounting for these two, typically what is done, the concept of variable geometry turbine, variable geometry turbine or turbines are developed. So, to circumvent the problem associated with the operation of fixed geometry turbine or turbines, variable geometry turbines are developed. So, let us now look into this particular type, and we can see that this is the variable geometry turbine. As such, this particular turbine or turbines are attached to turbocharger to have greater degree of flexibility of turbocharger operation. Let us now discuss about this particular turbine. So, what you can see from the schematic depiction is that this is essentially the extreme right component is the pneumatic actuator. So, this is pneumatic actuator, and if we look at the relatively larger component of this schematic, which is the cross sectional of turbine, view of turbine rather. So, you can see that there are a few rotating vents, that is why it is known as rotating vents, pivoting. So, these vents are pivoted on the ring. So, you can see these are basically rotating vents, and let me discuss about the hardware of this particular turbine, then I will discuss the operational procedure. So, these vents which are rotating, rather vents can rotate, these vents are pivoted on the ring, adjustable ring, because you can see that these are the adjustable, these are the rings. So, this ring is adjustable, and we can tune the operation of ring by this mechanical lever through this by this pneumatic actuator through this mechanical lever. So, this is mechanical lever. Right. So, and these blades are the fixed blades. So, these are the fixed blades or vents, fixed blades. So, as I said, these vents are rotating vents which are pivoted on the ring, which is adjustable, and we can control the passage between two consecutive rotating vents through this adjustable ring using this pneumatic actuator. So, pressure inside this pneumatic actuator is controlled by the engine control module. So, let me tell you one thing, if I write here this pneumatic actuator, this pneumatic actuator is controlled by the engine control module. Okay. Depending on the speed, this pneumatic actuator is operated. This pneumatic actuator controls the passage between two consecutive rotating blades using this mechanical lever. So, if there is a requirement or if the engine speed is high, as I said you in the previous class, when engine is suddenly accelerated, or if we need to develop more power from the engine speed will increase, then this pneumatic actuator will give some fit, this engine control module will operate pneumatic actuator. So, inside this pneumatic actuator, that air pressure is controlled by this engine control module. This pneumatic actuator controls the gap between two consecutive blades which are mounted on the adjustable ring using this mechanical lever, and through this exhaust gas or exhaust gases that is expelled from the engine cylinder is allowed to go into the turbine fixed blade through the passage from between two consecutive rotating blades. So, if we can control the gap between two consecutive blades, we can control the flow rate of exhaust gas or exhaust gases to be allowed to go into the inner part of the turbine, and if we can really have control over the flow rate of the exhaust gases, then we can also control the thrust that will be produced or the rotation of the this turbine inner blades, which in turn will control the rotation of the compressor. So, that way we can have greater degree of controllability of turbocharger operation using variable geometry turbine, and if we use this type of turbine, then problem related to the overspeeding and overheating which we have discussed in the context of fixed geometry turbine can be eliminated. So, this is the fixed geometry turbine. Now, let me tell you one thing, this is also known as pivoting vents turbocharger, which is or which are equipped with variable geometry turbine. And this is this type of variable geometry turbine or pivoting they are used in most common type in diesel engine. So, this turbochargers with variable geometry turbine is very common for the vehicle diesel engine. Now, let me tell you, so this is something which we can have some geometrical modification of the turbine itself. Now, even after having all these modifications, sometimes we may require fixed geometry turbine to be attached to the turbocharger unit. Now, in such a case, what we can do, we can really control the speed of the turbine having some mechanism, and that mechanism is known as that. Essentially, we have seen that pertaining to fixed geometry turbine, problems are over speeding and over. So, if we go to the next slide, so if we write fixed geometry turbine, two different problems, these problems are overspeeding, overheating. Even knowing these two different problems are there with this turbine, if we need to use this particular turbine in a turbocharging unit, then we need to have some mechanism to control these two to the extent possible. And one possible avenue is to bypass a portion of the exhaust gases that is expelled from the engine cylinder, right. So, let me tell you one thing, knowing these two different problems are inherent to this type of turbine, sometimes we may require to use fixed geometry turbine in a turbocharging unit. In such a scenario, what we need to do? We need to have some certain mechanism to have some control over these two problems to the extent possible. One possible avenue could be to bypass a portion of exhaust gases that is expelled from the engine cylinder so as to save the turbocharging unit. So, to safeguard the turbocharger from these two detrimental effects, when the turbocharger unit is having fixed geometry turbine, a portion of the exhaust gases that is expelled from the engine cylinder is deliberately made to bypass the turbine. So, what is done essentially, if I write bypassing the exhaust gases, not all, a portion of exhaust gases, right. So, this is what is needed. Now, if we need to bypass it, certainly we have seen that turbine, whether it is a fixed geometry turbine or it is a variable geometry turbine, turbine is installed at the exhaust manifold, because exhaust gases are liberated by the engine through the exhaust manifold into the ambience. So, certainly to have or to exploit or to employ or to utilize rather the maximum kinetic energy of the exhaust gases, turbine which will be used to rotate the turbine is placed at the location which is close to the exhaust manifold. Now, if we need to bypass, so what is done? A portion of exhaust gases is deliberately made to bypass the turbine housing. So, bypassing the exhaust gases, here what is done? A portion of the exhaust gas is deliberately made to bypass the turbine housing. Right. So, this is what is done. So, is made to bypass the turbine housing. That means, instead of allowing exhaust gases to go into the turbine, exhaust gases are allowed to go to the ambience through the exhaust manifold, right. So, if we go to the next slide, that means exhaust gases are directed towards the exhaust manifold, So, the exhaust gases a portion are not allowed to go into the turbine, and for that exhaust gas bypass passage that is opening. So, if we draw the engine cylinder, say for example, if it is the exhaust manifold, if it is the exhaust valve. So, if the turbine is placed over here, what is done? There will be one valve. So, that valve will allow exhaust gases to go into the ambience. Okay. So, this is the valve and this is the turbine. So, you can understand from the schematic depiction is that depending on the requirement, this valve is typically a poppet valve or any flap type valve. This valve will be operated by the diaphragm actuator, which is controlled by the exhaust gas pressure. So, this valve, which is the valve which is placed, this is either a poppet valve or any flap type valve. So, this valve is operated, and this is operated by diaphragm actuator. Okay. So, the valve is operated by a diaphragm actuator, and the diaphragm actuator is controlled by the exhaust gas pressure. So, this diaphragm actuator is controlled by the exhaust gas pressure. So, that means you can see essentially this valve is placed in the exhaust manifold. When we need to bypass deliberately a certain portion of the exhaust gases, this valve will be operated by a diaphragm actuator which is controlled by the exhaust gas pressure, and instead of allowing the exhaust gas to go into the turbine, certain portion of the exhaust gas is deliberately made to bypass to the ambience directly, and this bypass passage opening, which is also known as waste gate. So, if I use different color, so this is basically known as waste gate, that is the bypassage opening, because if we control this valve, this will open, and this waste gate will eventually control certain amount of a certain portion of exhaust gas to leave through the exhaust manifold into the ambience, so as to turbine speed can be controlled. So, that is what we wanted to discuss. That means, if we need to use fixed geometry turbine for any particular requirement, knowing fully that particular turbine, fixed geometry turbine will be having two different problematic issues. Rather, having one fixed geometry turbine in a turbocharging unit, there will be two problematic issues, and those are overspeeding and overheating. We can have this arrangement so as to prevent the turbocharging unit to the extent possible from these two undesirable phenomenon. Okay. So, with this, now let us solve one numerical problem on superchargers, and then by solving this numerical problem, we shall try to understand, or we shall try to illustrate the concept that we have learned on this particular unit, that is supercharger. So, if we go to the problem statement, let me read the problem statement first, then we shall start solving this problem. It is given an unsupercharged petrol engine, so it is not supercharged. So, this is naturally aspirated engine. An unsupercharged petrol engine develops 740 kilowatt of brake power with a fuel air ratio of 0.080, right. So, it is given unsupercharged means, you know, this is naturally aspirated engine, this is the brake horsepower and fuel air ratio is 0.080. So, this information we can see from the problem statement. The brake specific fuel consumption is 0.335 kilojoule per kilowatt hour. So, this is the BSFC, right, and mechanical efficiency is 78%, that is 0.78. The inlet pressure is 680 millimeter of mercury absolute and the mixture temperature is 320 K. So, basically, you know, inlet to the engine pressure of air and temperature of, you know, air fuel mixture is given as 320, that is the SI engine. So, typically for SI engine during intake stroke charge is drawn into the engine cylinder, that is air fuel mixture. As I told you, even for the modern CI engines, it is not only pure air that is drawn into the engine cylinder during intake stroke, rather there are, you know, there is a provision of supplying fuel in the intake manifold as well, because you know, nowadays multi-port fuel injection system is there, and hence it is not the pure air that is consumed during intake stroke, rather it is air fuel mixture or charge. So, the charge condition is given pressure and temperature. The engine is supercharged. So, next part of this problem is, if we you know, mark here, the next part of the problem is the engine is supercharged to a pressure ratio of 1.8 by a centrifugal supercharger of isentropic efficiency 75%. So, initially it is unsupercharged engine, next it is said that the engine is supercharged to a pressure ratio of 1.8 by a centrifugal compressor or supercharger. So, so by a centrifugal supercharger of isentropic efficiency 75%. We know in a supercharging unit only compressor is there, because instead of rotating a small turbine, compressor is driven by taking certain amount of energy from the output shaft of the engine, right. So, this is 75% and mechanical efficiency is 86%. Inlet to the compressor is same as those for the unsupercharged engine inlet. So, basically at the compressor inlet, even when it is supercharged, inlet conditions are same as what we had, you know, seen in the previous line. Assume that the fuel air ratio remains unchanged. So, fuel air ratio is remaining same and that IHP is proportional to the inlet density. So, this is again a clue. So, IHP will be produced by the engine is proportional to the density. Assume further that volumetric efficiency does not change. So, volumetric efficiency is also remaining same for these two cases. Calculate the BHP of the supercharged engine and its brake specific fuel consumption. So, these two we have to calculate. So, from this problem statement we had seen so many things, we shall discuss all these things again during the solution process, but what we need to calculate is the brake horsepower and brake specific fuel consumption during supercharged condition. So, let us solve this problem first. So, if we start solving this problem, so what we can do, first calculate the mass of or mass flow rate of fuel. Because if we can calculate mass flow rate of fuel, we know the air fuel ratio, then we can calculate mass flow rate of air. Okay. So, to calculate mass flow rate of fuel, we can use the information given. So, first case is naturally aspirated. So, this is keep in mind. So, first we are considering naturally aspirated case, that is when there is no supercharger. So, m dot f by definition, so you know initially it is given BSFC and BHP. So, m dot f divided by BHP, that is per unit kilowatt power developed, that is nothing but BSFC. So, m dot f is equal to BSFC into BHP. So, if we write, you know, BSFC is given 0.335 into this is given 740 kilowatt. So, it should be kg per hour. So, this is kg per hour, and if we just write the answer in terms of kg per second, so certainly it should be multiplied with 3600 and eventually it is coming as 0.0688 kg per second. Okay. So, this is the mass flow rate. So, calculating the mass flow rate of fuel, we can calculate mass flow rate of air. Air m dot A, because fuel air ratio is given 0.080, that is fuel air ratio. So, mass flow rate of air should be equal to 0.0688 divided by, you know, 0.080. So, mass flow rate of fuel divided by mass flow rate of air, that is the fuel air ratio. So, this is coming as, you know, 0.8607 kg per second. So, we have the mass flow rate of fuel and mass flow rate of air for the first case, that is naturally aspirated case. Now, for the naturally aspirated engine, if we write here, so for naturally aspirated engine, you know, we can easily calculate IHP. Why? Because mechanical efficiency is given, you know, that 78%. So, mechanical efficiency is nothing but IHP by you know, BHP by IHP, because brake horsepower is less than indicated horsepower. So, IHP should be equal to, that is brake horsepower BHP divided by eta mechanical. So, that equal to 740 divided by 0.78, that is 78% efficiency given, and if we calculate it, it is coming as 948.71 kilowatt. So, this is the indicated horsepower for the naturally aspirated engine. So, having calculated IHP and we know BHP, then we can calculate frictional horsepower, because IHP, that is the power produced inside the cylinder, BHP, that is the power available at the shaft. So, certain amount of developed power will be used to overcome the frictional losses, and that is FHP. So, if we calculate FHP for the naturally aspirated case, so FHP equal to IHP minus BHP. So, we have calculated these two. So, this is 948.71 minus BHP 740, this is kilowatt, and this is coming as 208.71 kilowatt. So, this is BHP. Now, what we will consider? We will consider, now consider supercharging. Right? We have discussed about the basic need of supercharging. Essentially, now the ambient air will be compressed by using a small compressor, and pressure will be higher and density will be higher. So, if we write for the case of supercharging for the compressor, so if I write for the compressor, you know, we can have this isentropic relation, that is T1s by Ti. 1s is the temperature at the exit of the compressor following isentropic compression, where I suffix I is or subscript I is used to denote the inlet quantity or inlet of quantities at the inlet of the compressor. So, this equal to we can write P1s by Pi power gamma minus 1 upon gamma, and from there we can write T1s equal to Ti into P1s by Pi power gamma minus 1 upon gamma, and it is coming as 320. This P1s by Pi, that is the pressure ratio. If we go back to the problem statement, it is given the engine is supercharged to a pressure ratio of 1.8. That means P1s by Pi, that is 1.8, and the value of gamma is given 1.35. So, this is 0.35 divided by 1.35. So, if we calculate it, it is coming as 372.6 Kelvin. So, here gamma equal to 1.35, that is given in the problem statement, and subscript I refers to the inlet conditions of the compressor, and 1s outlet conditions of the compressor following isentropic compression. Mind it, this actual pressure, actual temperature will not be the isentropic values. Okay. So, that you have calculated. Now, having all these, if we calculate actual temperature at the inlet of the engine. So, if we go back to the previous slide, so this T1s, this is not the actual temperature. So, this is the temperature at the exit of the compressor following isentropic compression, but actual temperature at the exit of the compressor will be something different, and for that we can use isentropic efficiency of the compressor. So, if we go to the next slide and if we write isentropic efficiency of the compressor, that eta compressor isentropic, that equal to it is T1s minus Ti divided by T1 actual minus Ti, right. So, here T1a is the actual temperature at the exit of the compressor, right, that we have discussed drawing HS, all the processes in HS plane, if you can recall correctly. So, let me draw this just for the sake of completeness. If we draw the compression process, so this is H, this is S, so this is Pi, and this is P1, so this is I2 1s, but actual process, compression process would be like this, and this is 1a, right. So, assuming the charge to be an ideal gas, to be precise calorically perfect gas, if we assume that Cp is constant, Cp is not a function of time, it is a function of temperature, we can have this. So, using this expression, that we can easily calculate T1a, that is nothing but Ti plus T1s minus Ti divided by eta compressor isentropic, okay, isentropic. And if we plug in the value, we will be getting 320 plus 6 minus 320 divided by 0.75, and it is coming as 390.15 Kelvin. So, this is the actual temperature. So, try to understand the temperature of the air at the exit of the compressor following isentropic compression was 372, whereas actual temperature is coming as 390.15 Kelvin. So, little higher. Okay. So, now what we can do, if we go to the next slide, it is given that according to the problem statement, you know, this IHP is proportional to rho, that is density, right. If we go to the problem statement, let me check again. It is given, you know, that IHP is proportional to the inlet density. So, that means this is rho I. So, from there for we can use some expressions. So, we can use the following expressions. And these expressions are IHP for the supercharged. So, suffix SC now refers to supercharged condition, while IHP NA, that is naturally aspirated. So, SC is for supercharged and NA, this is used for the naturally aspirated case. Okay. So, this is equal to rho I supercharged by rho I naturally aspirated. So, we can write rho equal to P, you know, 1, you know, by this equal to Ti. So, you know that inlet pressure is remaining same for both the cases, right, because inlet pressure is remaining same for the you know, so P1 by Pi and then into Ti by T1A. So, you know that for the supercharged, so this is basically the pressure ratio, right, and if I write it, we will be getting, so rho I equal to, so let me write here instead I can erase this I. So, this I can also erase, I also can erase. So, this will help you to understand this in a more. So, this is SC, this is NA, naturally aspirated. Naturally aspirated, so that is Pi by RTI. So, this quantity is basically Pi by RTI. R is remaining the same, while this SC is equal to P1. So, actual, because we are using compressor. So, that is P1 by RT1A. So, R will get cancelled. So, we are getting this. So, this is essentially 1.6 into Ti equal to 320 divided by actual, that we are getting 390.15, and if we calculate, so that is essentially the pressure ratio, and that we want using the supercharger, or that is compressor. And had we not used the supercharging unit, the temperature would have been 320, that is what is given in the problem statement. If we go to the problem, it is given 320 K mixture inlet temperature. Okay. So, if we calculate it, it is coming as 1.312. So, quickly if we can write, then IHP SC, that is supercharged condition, that equal to IHP naturally aspirated into 1.312. So, it would be coming as it is coming as, so it is 948 point, because we have calculated for the naturally aspirated engine IHP equal to 948.71 into 1.312, and it is coming as 1245 kilowatt. Okay, that is the case. So, if we go to the problem statement, just let me read a few lines. It is stipulated in the problem statement that volumetric efficiency does not change even after supercharging. Okay. Then mass flow rate of air remain constant for both the condition. So, volumetric efficiency does not change means the mass flow rate of air to the engines will be the same for both the cases, number 1. Number 2 is, if we consider this, so if we write here quickly, it will take hardly another 2-3 minutes. So, it is given that eta volumetric does not change due to supercharging, right. So, this means mass flow rate of air remains constant. For both the conditions. So, with this, with this consideration, we can calculate, with this consideration we can calculate the work input to the compressor. And that is W dot compressor would be equal to mass flow rate of air into Cp air into T actual temperature minus Ti divided by compressor efficiency, right. So, that is the work input to the compressor. In fact, we need to have, so what is compressor efficiency? Actual work input to the compressor should be always higher than the isentropic compression, right. So, isentropic compression to work done following, or rather actual work to be supplied to the compressor is the compressor efficiency. So, the work to be supplied to the compressor for the isentropic compression to the actual work to be delivered to the compressor, the ratio of these two quantities, the compressor efficiency. So, this is essentially actual work, So, the work done. Now, if we write here, it is coming as 0. Mass flow rate of air. Mass flow rate of air we have already calculated that it is not, that is 0.0688. So, that is the mass flow rate of fuel, and mass flow rate of air is 0.8607. So, if we plug in the value of 0.8607, Cp air is 1.00 5 kilojoule per kg Kelvin into this is 390.15 minus 320 divided by compressor efficiency is given 86%. So, if we calculate it, it is coming as 70.55 kilowatt, right. So, if it is the case, the net BHP of the superchargers engine. So, following this, then we can calculate the net BHP, that is brake horsepower of the supercharged engine of the supercharged engine, that is BHP SC equal to IHP SC minus FHP minus W dot compressor, because I said that for a supercharger this is the amount of energy which is borrowed from the output shaft of the engine to run the compressor, whereas for the turbocharger we have no need to borrow energy from the output shaft of the engine, rather kinetic energy of the exhaust gases is used to run a turbine. So, if we calculate it, it is coming as this is 1245 minus frictional horsepower is remaining same, that is 208.71 minus this is 70.55 kilowatt, and the total is coming as 965.74 kilowatt. So, this is the answer to the first part of this question, and if we calculate BSFC for the supercharged condition, that is again m dot f divided by BHP. So, mass flow rate of fuel is remaining same, that is given in the problem statement. So, this is 0.0688 divided by 965.74, and the unit should be if I write unit 0.2564, this should be kg per kilowatt hour. So, first of all you will get it in kg per kilowatt second, then multiply by 3600, then it would be you will be getting kg per kilowatt hour. So, this is the answer to the second part of the question. Let me go back to the problem statement once again. So, we had to calculate BHP of the supercharged engine and its brake specific fuel consumption, that is BSFC. And if we go to the last slide, then we can see these two, that is BHP of the supercharged engine and brake specific fuel consumption. So, what we have done in today's class, we have discussed about variable geometry turbines which are used to bring greater degree of flexibility in the turbocharging unit. Thereafter, we had seen that if we need to use fixed geometry turbine in some cases or in some situation, knowing fully that fixed geometry turbines are associated with detrimental or some undesirable phenomenon, then we have one possible way out to remove these two detrimental effects to the extent possible, and we have discussed this part as well. And finally, we have solved one numerical problem on supercharger, and by solving this problem we have tried to illustrate the conceptual part of this particular unit, that is supercharger. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.